Hello everyone and welcome to this video. Today I am going to be discussing feature importance. My presentation will begin with a brief motivation on the topic, followed by the significance of feature importance, which then will be followed by a brief explanation on the main two branches that we have to determine this metric with both substitution effects and without substitution effects. Finally, my presentation will conclude with parallelized and stacked feature importance. A common mistake in financial research is to run a machine learning algorithm with some data, backtest it, and repeat the procedure until a solid backtest appears. Repeating a test over and over can lead to false discoveries, and due to this, it can be considered scientific fraud. As an example, through this procedure, you can go even through 20 iterations until we find a false investment strategy that is subject to the standard significance level of 5%. Due to this, we have now feature importance, which is the main alternative to this procedure, which allows us to save both time and money. Having now gone through the motivation behind feature importance, we can now explore why it is so significant nowadays. So consider, for instance, that you have a pair of matrices containing features and labels for a particular instrument. We can fit a classifier, evaluate the generalization error, and achieve a satisfying performance. The next step would be to understand which features contributed to these good results. Through this analysis, we could add or remove features that allow us to improve the prediction abilities of our classifier and understand the patterns that were identified by it. And then with this, we would be opening up the so-called black box. Once we know which features are important, we can conduct more tests to learn more about our classifier. So we could analyze whether these features are always important and what may lead them to change through time, for instance. As mentioned during the introduction to this presentation, there are two main branches to determine feature importance. We have feature importance with substitution effects and without substitution effects. Beginning with feature importance with substitution effects, we must first define what these are. A substitution effect occurs when the estimated importance of one feature is reduced by the presence of other related features. So to say, these are the machine learning analogs of multicollinearity in the statistics and econometrics fields. To determine feature importance with substitution effects, we have two main methods. So we have mean decrease impurity, or MDI, and mean decrease accuracy, or MDA. Beginning with mean decrease impurity, we have that this is a fast explanatory importance in-sample method specific to tree-based classifiers. So, for example, random forest. At each node of each decision tree, the selected feature splits the subset it received in a way that the impurity is decreased. This allows us to determine for each decision tree how much of the overall impurity decrease can be assigned to each feature. Since we have a forest of trees, we can get the average for those values across all estimators and rank the features accordingly. As with every method, when working with MDI, we have some considerations to make. For instance, we must take into consideration that masking effects may occur when some features are systematically ignored by tree-based classifiers. We also have that every feature will have some importance even if they don't have any predictive power whatsoever. Then, we have that MDI cannot be generalized to other non-tree-based classifiers, and that it does not address substitution effects in the presence of correlated features. Finally, it has also been experimentally observed that MDI is biased towards certain predictor variables, in which an unfair advantage is given by impurity functions towards predictors with large number of categories. To conclude this section on mean decrease impurity, we will now be looking at an example. On the right, you can see this chart in which we have redundant, informed, and noise features. For each feature, we have an horizontal bar that indicates the mean MDI across all decision trees, and an horizontal line that represents the standard deviation. You can also see this vertical dotted line, which represents a situation in which we would have all features ranked equally. Overall, we can also say that NDI did a good job at classifying the features, as most informed and redundant features are above this threshold line. Moving on now to mean decrease accuracy, we have that this is a slow, predictive importance out-of-sample method. To implement this method, we fit a classifier, we derive the classifier's performance out-of-sample using a performance metric, for instance accuracy. Then we proceed to permutate each column of the features matrix, one column at a time, deriving the performance out-of-sample after each permutation. The importance of a feature is a function of the loss in performance caused by its columns permutation. As with MDI, we also have some considerations to make concerning mean decrease accuracy. For instance, we have that this method can be applied to any classifier, unlike MDI, which only work with tree-based ones. We also have that MDA is not limited to accuracy as its sole performance score, and that it is also susceptible to substitution effects in the presence of correlated features. Then, we also must take into account that it is possible that MDA concludes that all features are unimportant due to this being based on out-of-sample performance. Then, we have that the cross-validation must be purged and embargoed. Finally, we also have that when implementing this method, we may get that the improvement is negative, meaning that a given feature may be detrimental to the forecasting abilities of our machine learning algorithm. To conclude this section on mean decrease accuracy, we will also be looking at an example. Here on the right, we can see this chart in which we once again have redundant, informed, and noise features. Overall, we can say that MDA did a good job in the sense that most redundant and informed features are ranked better than the noise features. The main disadvantage of MDA is that the standard deviation is higher than with MDI, as you can see by the horizontal lines. Moving on to feature importance without substitution effects, we have that this can lead us to discard important features that happen to be redundant. This could lead us to the wrong conclusions when trying to understand, improve, or simplify a model. For this reason, single feature importance method can be a good complement to both MDI and MDA. Within feature importance without substitution effects, we have two main methods: single feature importance, which is a cross-section predictive importance method that computes out-of-sample performance of each feature independently, and orthogonal features, which we'll be discussing later on. When working with single feature importance, we have once again some considerations to make. For instance, we have to keep in mind that this method can be applied to any classifier, like MDA. We also have that SFI is not limited to accuracy as its sole performance score, and that no substitution effects take place, as just one feature is being considered at the time. Finally, and like with MDA, this method can conclude that all features are unimportant, as the performance is evaluated by auto-sample cross-validation. As for limitation of this method, we have that a classifier with two features can perform better than a bagging of two single feature classifiers. Finally, we have that joint effects and hierarchical importance are lost when using single feature importance. To conclude this section on single feature importance, we will be looking at an example. On the right, you can see once again a chart with redundant, informed, and noise features. Looking at the results, we can say that SFI did an adequate job. However, certain informed features are ranked worse than some noise features, most likely due to joint effects. This may be due to the fact that with SFI, labels are forecasted independently, which may lead to losing the joint effects. Finally, we can say that SFI can be used as a complement to both MDA and MDI, as these analyses are affected by different kinds of problems. Moving on to the other method to determine feature importance without substitution effects, we will now be looking at orthogonal features. So far, we've seen that substitution effects dilute the importance of features measured by MDI and underestimate the features measured by MDA. To compensate for these aspects, we can orthogonalize the features before applying MDI and MDA. For example, using principal component analysis doesn't fully prevent all substitution effects, but alleviates the impact of these. Using orthogonal features provides the following added benefits, namely that orthogonalization can be used to reduce the dimensionality of the features matrix, speeding up the convergence of machine learning algorithms. We also have that the analysis is conducted on features designed to explain the data structure. When discussing orthogonal features, there are some considerations that I would like to make. For instance, an overarching topic of this book is the risk of overfitting our machine learning model, as these algorithms will always find a pattern even if they happen to be a statistical fluke. Regardless of the method, be it MDI, MDA, or SFI, we should always be wary of the features that were identified as being important. So, for instance, if we carry out a principal component analysis, some features will be more principal than others, without any knowledge of the labels, ranking the features without any possible overfitting in a classification sense. Thus, if the MDI, MDA, or SFI analysis select as most important the same features that were selected by PCA as principal, then this confirmed that the pattern that were identified by the machine learning algorithm is not totally overfit. If this wasn't the case, there would be no correspondence between the principal component analysis ranking and the feature importance ranking. Having now addressed substitution effects, we can move on to the last topics for this presentation: parallelized and stacked feature importance. Beginning with the former, we would have for each security in an investment universe that we would form a dataset and derive the feature importance in parallel. Features that are important across a wide variety of instruments would be more likely to be associated with an underlying phenomenon. What are the advantages of this approach? Well, namely, it can be computationally fast as it can be parallelized. However, there are some disadvantages. For instance, due to substitution effects, important features may swap their ranks across instruments, increasing the variance of the estimated feature importance. Moving on to stacked feature importance, we have that this strategy consists on stacking all datasets into a single combined dataset. The purpose of this approach is to ensure some distributional homogeneity. Through it, the classifier must learn which features are more important across all instruments simultaneously, as if the entire investment universe was a single instrument. As with all approaches, we have some advantages and disadvantages. For advantages, we have that the classifier will be fit on a much larger dataset than with a parallelized approach. We have that importance is derived directly, and that conclusions are more general and less biased by outliers or overfitting. Since importance scores are not averages across instruments, substitution effects do not cause dampening of these scores. Finally, for disadvantages, we have that using feature stacking approach may lead to a significantly greater consumption of computational resources. To conclude this presentation, there is one last consideration that I would like to make. As stated by Marcos Lopez de Prado, we have that backtesting is not a research tool. Feature importance is. This is something that we will always have to keep in mind when validating our models. And with this, I conclude my presentation. Thank you for staying with me through it. I hope you found the topic as interesting as I did, and I look forward to seeing your comments down below. And yeah, see you in class. Thanks.